Good morning, and welcome to my talk at Sigmafine Virtual Summit 2020. My name is Todd McQuiston, and I'm a Senior Systems Specialist with Hemlock Semiconductor in Hemlock, Michigan. That delightfully vague job title hides that I'm a system administrator of a few different platforms and technologies at HSC, Pi and Sigmafine being the two major ones. Pi System at Hemlock Semiconductor is the backbone of our site. We have users across the organization, from maintenance and operations to finance and research. We have long used Pi for production recording, and in the earliest days of merging the two, data from Pi was simply used by the operators in various production areas to input the production and consumption quantities each shift. We did this with basic Pi ACE equations. Later, we started using Sigmafine to give us a more in-depth mass balance analysis of the entire plant, taking a more holistic view of our calculations. Sometimes it's actually better to look at a task as one big job instead of 972 small ones. Having done that, our next step was to take the results given to us by Sigmafine and send them directly to our ERP system, which is now SAP S4 HANA. Today, I will give you a quick overview of Hemlock Semiconductor and the silicon market, talk about our Pi and Sigmafine system, our main Sigmafine models, and how we managed to integrate Sigmafine with SAP. Hemlock Semiconductor was founded in 1961 and was originally a partially owned subsidiary of Dow Corning Corporation. After nearly 6 decades and the changes that have taken place in the chemicals industry, we are now primarily owned by Corning Incorporated, and Shinetsu Hondatai holds a minority stake in our company. We are currently the largest producer of polycrystalline silicon, also known as poly, in the United States. The silicon made at HSC is of extremely high quality, and if all those digits make you dizzy, our silicon is pure to approximately 10 parts per trillion. Our silicon is produced in large batch reactors using chemical vapor deposition. There are many intricacies in the preparation and mixing of the reactor feed, but once the material is in the reactor, things get very simple. The reactor is heated to thousands of degrees Fahrenheit, and at that temperature, the silicon-bearing molecule in the feed, trichlorosilane, pretty much falls apart. The remaining hydrogen and chlorine atoms are reacted with fed hydrogen to produce hydrogen chloride gas, which is then recovered and recycled to again create more trichlorosilane feedstock in another process. Our site produces semiconductor and solar grade silicon via the same process. Solar grade generally has lower quality specifications from our customers, which for us means it can be produced slightly more quickly in the reactors. Our site's reactor buildings are allocated to making either semiconductor grade or solar grade silicon. Some of the chemicals which get created in the overall process by incomplete reactions and so on are sold as products. Silicon tetrachloride, used in the production of fiber optic cable, is one example of this. Silicon takes a fairly complex path going from sand to microchips, but here's a quick explanation. We start with metallurgical grade silicon, which is generally around 98% pure. The impurities are mostly iron, but boron and phosphorus are also present. That metallurgical silicon is reacted with hydrogen chloride to produce trichlorosilane, which is the primary feed material to our CVD reactors. These last two steps are performed at HSC. Polycrystalline silicon is then produced in our reactors. Our customers use that poly to create single crystal silicon. In a process which is nearly as much art as science, the poly is melted in quartz crucibles, a seed crystal is introduced, and a log is drawn upward from the molten silicon. The log is a single perfect crystal with no grain or variation anywhere in it. The logs, which are anywhere from 150 to 450 millimeters in diameter, are sawed into wafers. These wafers are then sold to microchip manufacturers such as Intel, AMD, and Infineon, where chips are etched onto them via photolithography. An increasing proportion of produced silicon is going to the photovoltaic market for use in producing solar cells. The growth in this market has spurred expansion at our site over the past 10 years. Currently, approximately 80% of the world's supply of poly is used in the making of solar cells. While microchip demand is higher than ever, advances in the technology, such as larger wafers and smaller transistors, have yielded a net decrease in the amount of silicon needed. Despite that, It is estimated that 1/3 of all microchips being produced are using HSC silicon. However, has become a simple fact in the last 20 or so years, a company is its data. How does HSC handle its data? HSC extensively makes use of the Pi system, which should come as no surprise to anyone here. Most users of Sigmafine are companies which have wrung all of the functionality they could from their Pi systems and need just a bit more. Having started using Pi in 1993 with Pi 2 on VMS, we started with the tools available at the time and have upgraded where possible over the years. Every one of our dozens of reactors is configured in Pi batch generator, and they started as units in the Pi batch subsystem. We are working to convert everything to event frames, and the standardization of our reactor configuration across this site is making this a far less daunting task than first anticipated. We also have a large installed base of Pi-ACE equations. We are working to convert where we can to asset analytics, but we also have a great deal of custom code, which requires the functionality available in a .NET-based container. Our site's control system is an 800XA by ABB, which we use with OPC, HDA, and DA to extract data from it. Because of HDA's backfilling nature and how it interacts with the 800XA, all critical and Sigmafine related tags are collected by OPC DA interfaces. Our primary visualization tool is still a process book on site, but outside of the production areas, TIBCO's Spotfire is becoming the app of choice due to its extensive available integration with AF and other systems. We brought our Sigmafine models online in 2014. The installed version was 4.5.3, and that is what we're still running. The AF foundation of Sigmafine 4.5 is AF 2010, which has been superseded many times since then. We are planning to upgrade soon to version 4.7. We have 3 active models running on our server, 2 trailer receipt models to move raw materials into our inventory, and the main model, which is the basis for all examples and screenshots in this presentation, is a mass balance of the entire site, all our reactors, fluid beds, tanks, and distillation trains. It has approximately 4,500 elements in it and is the result of many years of work, accommodating plant expansions, changes, and even contractions. So what made us want to integrate Sigmafine with SAP? Did we look at Sigmafine and say, nah, not complex enough. We need to really complicate this? Not quite. HSC had long been a user of OSIsoft's PS R-Link. For those who are not familiar with R-Link, it could possibly be thought of as OSIsoft's original integrator to ERP systems. There were a few variants of R-Link, SAP, Maximo, and more, and their function was to permit the interchange of Pi and ERP data. HSC started using R-Link around 1997 in concert with our calculation engine to provide once per shift production and consumption values of various processes and materials. This initial implementation saved approximately 10 man-hours per week per process and reduced errors by more than 80%. That doesn't sound like much, but Dow Corning and HSC together had many processes, so those savings added up quickly. However, R-Link was extremely difficult to configure and support. Only a few people at OSIsoft were trained to support it, so all users quickly had to become their own experts. We needed a new solution. Enter Sigmafine. Okay, everyone, buckle up. I would like to take this time to show you the architecture of our Sigmafine system and how it all fits together with Pi and SAP. As always, we start with Pi. All process data is being written to our production Pi collective. Also in this picture is our SAP instance and Sigmafine server, of course. To the standard Pi Sigmafine architecture, we have added 2 major parts. One is a SQL server. This SQL server is the host of the Pi and Sigmafine servers' AF SQL databases. However, it also hosts a custom database called, appropriately enough, HSC Sigmafine. This database is a storehouse for case data, transaction information, and anything else we want to track that wouldn't normally be logged by Sigmafine. We'll go into detail on some of those tables later in this talk. The other extra piece is the TIBCO server, multiple servers behind a load balancer in our case. TIBCO supplies a number of web services which can be used to communicate synchronously with SAP. We use those services to send our transactions to our SAP instance. When the Sigmafine case runs, it pulls data from Pi, case history from the SQL server, and inventory levels from SAP. Based on the results of the case, transactions are prepared. The transactions are sent to the TIBCO server. The TIBCO server sends the transactions to SAP and receives confirmation of the transaction's success or failure. Transaction status is written back to the SQL Server transaction table. Once all the transactions are done, Sigmafine writes the case status and info back to the SQL Server. Finally, the case results are written to Pi. I'd also like to note that there are some other SQL servers which we access for data from Sigmafine, and they are not shown on this diagram. After this last slide, you may be wondering, what is doing all this? Is this hidden functionality in Sigmafine? No. We have written a custom AF SDK application which handles all the SAP and TIBCO related work. This runs in the background and is triggered by Task Scheduler on the Sigmafine server. We have also developed a console version of this application, which permits users to manually step through the Sigmafine case and see the results in real time. Users can still use the Sigmafine add-in for the Pi System Explorer to run cases, but doing so will not run the custom app and execute any SAP-related procedures. This is just a quick comparison of the user interface in our app and the one we all know from the Pi System Explorer. We tried to make them as similar as possible. One of the minor things our code does is write the final status of the case, its fail success status, and which step it finished in the run to the description field. Custom interface shows that our process has more steps, 10 versus the default 5, but most of them happen after the publish step. The extra one that happens before is Pi tag validation. In this step, every Pi tag is tested for good current values, an adequate % good over the time frame of the case, and any other tests we may want to add, high and low validation, for instance. Each test type is assigned a severity, and failure will issue a warning or an error. When an error occurs, the case is stopped, and an email is sent to the named system engineers and/or admins, listing which tag or tags had the error and why it failed. If the error is fixed, the next case will run as planned, or a case can be manually executed if the admin wishes. So, how did we do this? Thanks to Sigmafine being based on Asset Framework, all the tools were handed to us. Instead of having to take a scorched earth approach and start from the ground up, we just modified the element templates supplied by Sigmafine. In most cases, our custom attributes only exist on templates derived from a default Sigmafine template. To make the modifications easier to identify, we implemented some basic housekeeping. All new SAP-related attributes start with Z_SAP. We also built some custom data references to go along with the new data references supplied by Sigmafine. We implemented a couple custom data references, but the workhorse of the collection is the SQL query. This data reference takes as its input a connection string and a SQL query. The result of that query is then written to the value of the attribute. This reference supports trusted or untrusted connections. This is key, as some of the SQL servers we access and the Sigmafine server are separated by a firewall and located on two different domains which do not share a trust. So Active Directory authentication is not possible. It supports multiple query types. Select, update, and delete are all supported. Linking a table in AF and using the table lookup data reference effectively only supports select queries, which limits us significantly. Also, some of the tables that Sigmafine talks to update very frequently, which could increase overhead on AF if the table were to be brought into the library. As you can see, the SQL Server database is an important piece of the workflow in this process. But what exactly are we keeping in it? The database contains multiple tables: cases, inventory, transactions, movements, process orders, tag validation results, and more. Each table is indexed by the case ID, which is generated in the cases table and referenced in the AF database on the Sigmafine server. The cases table is also a critical part of the modified scheduling we've added to our models. Because our cases write to SAP and update our site inventory levels, every run is critical. More to the point, the data generated by every run are critical. Our main mass balance model runs every 3 hours. The two trailer cases run hourly and daily, respectively. We've settled on this interval as a happy medium. It keeps the amount of data to be processed to a reasonable level, but is long enough that a transient pi tag problem, such as instrument maintenance, can self-correct between runs. Each site mass balance run takes about 9 minutes, but this is artificially extended as the application waits for 2 minutes once the SAP transactions are sent to give them time to complete. But since the transactions are only for the time frame of the case, 3 hours ideally, if a case is missed, we could potentially lose the data in it. Let me make it clear, we did not develop a new scheduling engine which replaces Sigmafines. The custom application works in tandem with the Windows Task Scheduler. There are simply 8 entries to run the mass balance model every 3 hours over the course of a day. Every time a new case runs, the application sets the start time of the new case to the end time of the last successful case, plus 1 second. This functionality allows us to do maintenance or other server work on Pi or Sigmafine without worrying about impacting the integrity of our SAP transaction data. The cases table on the SQL Server assigns a case ID when it is built, which is then used for all references to that case across the SQL database and in Sigmafine logs. It also stores key information about the case itself, whether it completed, its last successful step, who created the case. Manually created cases will list a user AD account, and scheduled cases will list the service account, and the start and stop time of the case. As I had mentioned previously, every time the .NET app starts a new case, the first thing it does is read this table and find the last case with a completed status of 1. It finds that case's end time, adds 1 second to it, and that becomes the start time of the current new case. It will keep doing this until a run completes successfully. So, in our example, you can see that the cases in lines 204 and 205 failed at step 3. In line 203, it succeeds. Now, if you look at the start time for lines 203, 204, and 205, they all list the same time. So when it finally succeeds, the case in line 203, case 108420, covered 9 hours worth of data from noon to 9 p.m. on September 2nd. We also log every transaction sent to SAP via the TIBCO web services. This table generates a unique ID for each transaction and attaches to it the case ID of the source run, status of the transaction, 1 is a success and all negative values are error codes, the SAP ID of the related material, the SAP transaction type, most of them are 101, 261, or 531, quantity, which I don't have shown here, and the AF element in the model to which this quantity refers. If a transaction fails at the SAP or TIBCO level, its status will be set accordingly and not processed. They will not automatically be processed when the issue is resolved. This permits the proper people, logistics personnel usually, to examine them and make sure they look right before sending. Once approved, the admin sets their status to a specific value, which signals the application to reattempt processing. In summary, Hemlock Semiconductor is still relatively new to Sigmafine. We assigned it one major task and made that task as complete as possible. However, Sigmafine offers far more than simple mass balances. We are looking forward to building some new models and incorporating component balances where useful. Basing Sigmafine on AF is the key aspect that made this project possible. Without it, we would have been stuck with more or less writing a full replacement of Sigmafine, which did our extra SAP work, but the underlying mass balance would not have been as robust or accurate. As any developer knows, trial and error is part of the process. We were lucky in that we were running PSR Link and were generating numbers against which we could compare the results of our then development Sigmafine model. We do plan on upgrading Sigmafine soon and seeing what is improved and what tasks can be turned off in the custom code. Despite all this work I've shown you, we always prefer to have vendor-supplied solutions do as much of the work as possible. With that, I'd like to thank you for your time and attention. I will be available in the Q&A session following this presentation.